Right. So basically what we discuss in this chapter is a few models of the atom and how they explain certain experimental observations and how they don't explain some observations. Okay, so merits and merits of a few models of the atom. Now, experimentally, it was found that gases, they emit negative charges, and J.J. Thomson performed experiments and found out that these negative charges are basically nothing but electrons. So there was evidence that there are negatively charged particles in atoms. Now, the atom is neutral and there are negative charges, means there should also be positive charges. So J.J. Thomson came up with a model of the atom, which is called the plum pudding model, okay, or the watermelon model of the atom. So basically what he said is that the positive charge in an atom is distributed all over the atom, with the negative charge distributed like the seeds in a watermelon. Okay. So the flesh of the watermelon is the positive charge and the seeds of the watermelon are the negative charge. This is the model that he proposed. Uh, but there is a fundamental flaw with this. Why do the positive and negative charges stay like that? Okay. Positive, negative should combine, they should become neutral. Okay. And it was also found that atoms emit radiation. Okay. And this model could not explain why atoms emitted radiation and such things. So basically, this is a failed model. Next, Rutherford suggested some experiments to find out what is there in an atom, or he suggested some experiments to determine how the positive and negative charges were arranged in an atom. Okay. And two scientists, Geiger and Marsden, performed the experiment that Rutherford suggested to find out what is there in an atom. Okay, experiment, it's called the alpha ray scattering experiment. Basically, what they did is they made an alpha ray. Okay, what is an alpha ray? A collection of alpha particles. Okay, they made an alpha ray incident on a very thin gold foil. Okay, the gold foil was so thin that the width of the gold foil or the thickness of the gold foil is approximately equal to the size of one atom of gold. Okay, it was that thin. So it was less than 1 micron actually, the thickness of the gold foil. So they considered an experimental setup like this. Fine. Using a radioactive substance, they created a stream of alpha particles. Okay. You will learn in the next chapter, nuclei, that radioactive substances undergo alpha decay. They emit alpha particles. Okay. So they created a stream of alpha particles. That is what we call as an alpha ray, which was targeted towards a gold foil, a very thin gold foil. So basically the aim was to find out to see what happens to the alpha rays, and based on that, explain what is present in an atom. So when an alpha ray is pointed towards a gold foil, you can see, like, this is basically what they found in the experiment. You can see that most of the alpha rays pass through the gold foil without much scattering. Okay. They continue in their own direction or get deviated by a very small angle. Very few alpha rays. Okay. How few is very few? About 1 in 8,000 or even less than that. Okay. Alpha particles were found to undergo a deflection of more than 90 degrees from the gold foil. Okay. And very, very few, about 1 in 10,000 or maybe even less than that number of alpha particles were found to retrace their original path. Retracing the original path means going straight towards the gold foil and coming back along the same path. Okay, a very, very small fraction of alpha particles was found to do that. Most of them passed without deviation, very few passed with significant deviation, and an even smaller fraction undergo a deviation of 180 degrees. Okay, so they even plotted a graph of the fraction of alpha particles versus the deviation that they suffer. Okay. On x-axis, you take the deviation, and on y-axis, the fraction of alpha particles. So most of the alpha particles, wait, if you plot fraction, then that will be a large fraction. Let's take the number itself. No, fraction is also fine, no? Yeah. Yeah, most of the alpha particles pass without deviation. Means theta is equal to 0, the fraction will be large, and greater angles, the fraction of alpha particles which suffer deviation of greater angles is smaller and smaller. So the graph kind of goes like this. Okay. Now, based on the fact that only about 1 in 10,000 or even lesser than that number of alpha particles undergo a deviation of 180 degrees, what they proposed, okay, is that atom must be largely empty. So if you consider this as the space in an atom, okay, because most of the alpha particles pass without any deviation, they concluded that most of the atom must be empty, and there are some alpha particles undergoing some deviation. There is a very small fraction of alpha particles undergoing a significant amount of deviation also. So what they said is the positive charge that is present in an atom must be present in a very small space, okay, compared to the actual volume of the atom. All the positive charge must be present in a very small region. How did they conclude that? See, an alpha particle is being sent back, okay, or is getting deflected by 180 degrees, means it has come across a positive charge in its path. Alpha particles are positively charged. When will a positive charge deviate by 180 degrees? When there is another positive charge straight in front of it. Okay. So suppose this is an alpha particle. Assume it is moving to the right. If there is a positively charged object present in its path, fine, alpha particle is positively charged, that other particle or object is also positively charged, then what will happen? The alpha particle will slow down further, stop at a certain distance, and then due to repulsion, it will go back along the same path. Now, this was found to happen with a very small fraction of alpha particles. So they concluded that all the positive charge that is there in an atom must be present in a very small region of the atom. And that small region of the atom is what was called as a nucleus. Okay. And the negative charge is distributed in the space around the nucleus. Now, negative charge cannot simply be at rest close to a positive charge. So what Rutherford proposed is that the negative charge in an atom, okay, the electrons that are present in an atom must be revolving around the positive charge. Now see, this is an angular view. If you look at it from straight in front, it appears like this. Okay, the negative charge present in the atom, or the electrons present in the atom, must be revolving around the nucleus, just like planets revolve around the sun. Now planets revolve around the sun under the influence of gravitational force. And Rutherford proposed that electrons revolve around the nucleus. Nucleus is positively charged, electron is negatively charged. They revolve around the nucleus under the influence of electrostatic force of attraction. See, for revolution, for any object to go around in a circle, a centripetal force is necessary. So he said that that centripetal force is nothing but the electrostatic force of attraction between the nucleus and the electron. Okay. So since he said that electrons revolve around the nucleus like planets revolve around the sun, this is called the planetary model of the atom. Now, because electron is revolving around the nucleus, it explains why the positive and negative charges don't combine and the atom, and they become neutral. Okay, it doesn't, uh, I mean, it eliminates that possibility. Okay. Now, the alpha particles which are directed straight towards the nucleus, they slow down, stop, and go back along the same path. Fine. What about the other alpha particles? Now, you assume this is the nucleus, positively charged nucleus. And let's say the nucleus has Z number of protons, then its charge will be plus Ze. Okay. The alpha particle which is directed straight towards it suffers a deviation of 180 degrees. Okay. It stops somewhere along the path and turns back. If you consider some other alpha particle, okay, now what was generated was a parallel beam of alpha particles. Fine. So if you consider another alpha particle which is incident towards the gold foil like this, now this other alpha particle, it's the line of action of its velocity, as you can see, misses the nucleus by a certain distance. This distance is called the impact factor. Sorry, impact parameter. Okay. The distance between the line of action of velocity of an alpha particle and the nucleus of the gold foil, that is called impact parameter. Now, we can number these alpha particles. This is the first one. This is the second one. For the first alpha particle, impact parameter is 0. And if impact parameter is 0, what happens? You get maximum deviation of 180 degrees. Okay. The alpha particle, which is projected this way, goes straight and comes back along the same path. So if impact parameter is 0, the deviation suffered is 180 degrees. Fine. As the impact parameter increases, now imagine this alpha particle, the second alpha particle going towards the nucleus. At some instant, let's say it is at this position. Okay. Assume the repulsion from the nucleus was not that significant till there. So it traveled in a straight line, almost a straight line. Now when it goes quite close to the nucleus, the repulsive force of the nucleus starts becoming significant. Now this particle, this alpha particle's velocity is to the right. Okay. But it experiences a repulsive force from the nucleus and that will be directed away from the nucleus. So repulsive force will be in this direction. Force and velocity not along the same line, so the particle will deviate from that line. Fine. Let's say it deviates and goes somewhat like this. When it comes to this position, it's even closer to the nucleus, so it will experience an even stronger electrostatic force of repulsion. Force is in this direction. Its velocity was this way, but force is in this direction. As a result, it gets deviated even further and so on. So you will see it following a path somewhat like this. So the original direction in which it was traveling is this, and the final direction in which it is going is somewhat like this. This is the angle of deviation for that particle. And you can see it's less than 180 degrees. So as the impact parameter increases, the deviation decreases. Okay. So this is the path followed by one of the alpha particles. This is the path followed by another alpha particle, some of the alpha particles, and so on. As you increase the impact parameter, the deviation decreases. So some alpha particle may follow a path like this. Farther it is from the nucleus, lesser the repulsive force that it experiences, lesser the deviation that it suffers. That's the idea. This way. Okay, so different alpha particles will suffer different amounts of deviation. Fine. Now, alpha particle is nothing but a helium nucleus. So suppose one alpha particle is directed straight towards the nucleus. The charge of an alpha particle is plus 2e because it has 2 protons, 2 neutrons. The proton's charge will be e, 2 protons, 2e. Assume it is directed straight towards the nucleus. Let's say the atomic number of the nucleus is Z. So its charge, positive charge will be plus Z. There are neutrons also inside it. But from the protons, the positive charge it gets is this much. Okay. Now, alpha particle is a helium nucleus. It has 2 protons, 2 neutrons. That's all. They are incident towards what? In the gold foil scattering, alpha ray scattering experiment, they are incident towards a gold foil. Now, gold has quite a large atomic number. How much is the atomic number of gold? Anyone? Atomic number of gold. Okay, fine.
It's
Huh?
79, I think.
79. Correct. Correct. Okay. That means it has 79 protons. And in addition, there will be 79 or more neutrons also. So it's quite heavy compared to the alpha particle. Okay. So when an alpha particle is incident towards a gold nucleus, since the gold nucleus is a very heavy object compared to the alpha particle, very heavy particle compared to the alpha particle, you can assume it relatively remains at rest. Okay. The gold nucleus does not move. Now, as this alpha particle approaches the gold nucleus, it will slow down due to electrostatic repulsion and it will stop somewhere. Okay. This is called as stopping distance. Let's say the shortest distance between the alpha particle and the gold foil is small d. Now, where is the alpha particle incident from? A very large distance compared to their sizes. The distance from where the alpha particles are projected is very large. You can assume initial distance to be infinity. Okay. The final distance, that is the shortest or the closest it gets to the nucleus, let it be d. Fine. Now, you should be able to calculate that closest distance, the shortest distance of approach between an alpha particle and the nucleus. Now, let's say alpha particle's charge is 2e and assume its mass is capital M. Fine, it has 2 protons, 2 neutrons. You can tell how much its mass is also, but let's assume it is capital M. And let's say it is projected towards the nucleus with a speed u. Okay, from a very large distance. Now, you know it slows down and stops somewhere. Find out the shortest distance of approach. Find out how close it gets to the nucleus. Answer will be in terms of E, Z, capital M, okay, and Coulomb's constant K. Okay. Try this. Derive the shortest distance of approach between the alpha particle and the nucleus. Any idea how to solve this? How to find out the shortest distance of approach? See, you know the speed of a particle at one position, and you know the speed at another position also. You know initially how far it is. You need to find out how far it is finally. So you need a relation between speed and position, okay, or speed and displacement. Now this slowing down of the alpha particle is happening due to electrostatic force of repulsion from the nucleus, and electrostatic force is a conservative force. Therefore, you can apply conservation of mechanical energy to solve such problems. How do you apply conservation of mechanical energy? Initial potential plus kinetic energy should be equal to final potential plus kinetic energy. Okay. Now these are 2 point charges. Alpha particle having a charge 2e, nucleus having a charge Ze. And potential energy between 2 point charges, electrostatic potential energy, is given by K Q1 Q2 divided by the distance. So K, Coulomb's constant. One charge is a charge of the alpha particle 2e. The other charge is charge of the nucleus Ze, k q1 q2 divided by initial distance between the charges tends to infinity. Okay. Plus kinetic energy. The alpha particle had kinetic energy half mu square is equal to final potential energy. Finally, let's say the alpha particle gets to a distance d from the nucleus. Then the final potential energy will be k q1 q2 divided by the distance d. And it stops at that distance, so final kinetic energy becomes 0. So initially the potential energy is 0 because it is at infinite separation. Finally, the kinetic energy is 0 because it stops. That's all. From there you get the distance d. So d becomes 2 goes to the other side, gets multiplied 4 kz e square divided by mu square. Okay. So if you know the speed with which the alpha particle is projected exactly towards the nucleus, straight towards the nucleus, this is the shortest distance it gets to. Okay. The closest it gets to the nucleus. Simple energy conservation is what we use. But there are many different ways of asking you this question. Here, I gave you the speed of the alpha particle and asked you to find out how close it gets. Instead of giving you the speed of the alpha particle, they can give you the kinetic energy directly. If they give you the kinetic energy directly, substitute it directly here. Then what does the answer become? You get d is equal to 2kz e square divided by the kinetic energy of the alpha particle. This is also another way to express the distance. And they can even tell you the de Broglie wavelength of the alpha particle. Okay, that is another way of asking you the question. Suppose they tell you that the alpha particle has a de Broglie wavelength of lambda. Okay, now what is the formula for de Broglie wavelength? Lambda is equal to h by mv, the momentum of the particle. So h by p you can write. You can also write it as h by under root 2m kinetic energy. Okay, where m is the mass of the object, k is kinetic energy of the object. Now, if they give you the de Broglie wavelength and ask you how close it gets to the nucleus, see, the method is still conservation of mechanical energy only. And in conservation of mechanical energy, you are supposed to express kinetic energy, substitute kinetic energy. So from lambda, from de Broglie wavelength, you will get the kinetic energy of the alpha particle. Okay. How do you do that? Square it on both sides first. You get lambda square is equal to h square by 2m ke. Therefore, the kinetic energy of the alpha particle turns out to be h square divided by 2m lambda square. You will substitute that in place of ke here. H square divided by 2m lambda square, and you will get d in terms of that. So you can be given the de Broglie wavelength of the alpha particle initially and asked how close it gets. This is how you deal with it. There's another way also to ask the same question. You can be given the potential difference by which the alpha particle is accelerated. Okay, delta V. What do we mean by accelerating alpha particle by a potential difference? Basically, the charge going through a potential difference, that's all. Alpha particle is a charged particle. When you make a charge go through a potential difference delta V, okay, a charge Q goes through a potential difference delta V, then it gains a kinetic energy of Q delta V. So alpha particle's charge is 2e, right? Assume it is made to go through a potential difference delta V, then the kinetic energy it gains will be 2e delta V. So in place of kinetic energy, you substitute that and you can get the shortest distance of approach. So there are many different ways of asking you this question. Right? And in any case, the concept you apply is mechanical energy conservation. So you should somehow find out the kinetic energy of the alpha particle initially and substitute it in the mechanical energy equation. Right. So this is the atomic model that Rutherford proposed. Okay, Rutherford planetary model of the atom. He said all the positive charge that is there in an atom is present in a very small part of the atom called the nucleus. How small is the nucleus? The radius of the nucleus is approximately 10 power minus 5 times the radius of the atom. Okay, in your textbook they have given a comparison also. if you consider the size of the atom as a normal room that you see, okay, then the size of the nucleus relative to that atom is like the tip of a needle. Okay, the pointed tip of a needle. That is how small the nucleus is compared to the atom. Okay, like you can I mean, you can do those calculations on your own also. 10 power 5 times is the 10 power 5 is the factor, right? So suppose you consider the nucleus as nucleus to be 1 millimeter wide. Okay, you know how much 1 millimeter is. So suppose the radius of the nucleus is 1 mm. Okay, then the radius of the atom will be 10 power 5 times of that. So 10 power 5 into 1 millimeter, that is 100 meters. Okay, 100 meters is almost like the length of a street. So if you take the size of the nucleus to be 1 mm, then radius or diameter, anything. Suppose you took diameter to be 1 mm, then the diameter of the atom will be 100 meters. It is of I mean, it is that large compared to the nucleus, or the nucleus is that small compared to the atom. The atom has that much empty space. Okay. Now, there are some problems with this model of the atom. This atom explains why the negative charge doesn't mix with the positive charge, because it is revolving around it in orbit, circular orbits. That's fine. But see, anything which is revolving in an orbit, okay, or any object which is revolving is accelerating. To move in a circle, acceleration is compulsory. So basically, this electron in the planetary model of the atom is an accelerated electron. Okay. And we discussed in the chapter electromagnetic waves that accelerated charges radiate energy, okay, in the form of electromagnetic waves. So what should happen is this electron which is revolving around the nucleus should continuously emit electromagnetic radiation and lose energy. And if the electron loses energy, what should happen is it should slow down. And if it slows down, the electrostatic force of the nucleus will pull it in. So the electron should lose energy, slow down, and spiral and fall off into the nucleus like this. Okay, according to electromagnetic theory, this is what should happen. Rutherford's atomic model could not explain why the electron does not radiate energy. Okay, so that is one of the drawbacks of this model. Why an electron does not radiate electromagnetic waves and collapse into the nucleus. Okay. Another thing it could not explain is something called atomic spectra. Okay. This is probably the most important part of this chapter, atomic spectra. Basically, what is an atomic spectrum? Atoms emit radiations of certain wavelengths only. Okay. And atoms also absorb radiations of certain wavelengths only. For example, if you fill a tube with hydrogen, okay, and incident radiation on it, radiation of multiple wavelengths on it, you will see that that tube of hydrogen, okay, absorbs only certain radiations that fall on it. It doesn't absorb all the radiations. Fine. The set of wavelengths which the particular atom absorbs is called its absorption spectrum. Okay, there's something called an absorption spectrum. The wavelengths that are absorbed by an atom. And atoms have something called emission spectrum also. An atom which has been energized, okay, means supplied with energy, loses that energy by emitting radiations. This has all been determined experimentally, okay, observed experimentally. So excited atoms or energized atoms, they get de-excited or lose their energy by emitting radiation. But they don't emit radiation of all possible wavelengths. They emit radiations of only certain wavelengths. Okay? That is called the emission spectrum of an atom. That's the set of wavelengths that are emitted by an atom. Rutherford's atomic model does not explain why only certain wavelengths are absorbed and why only certain wavelengths are emitted. So these are the two drawbacks of this model of the atom. If you consider the atom to be like this, let's say there is a nucleus having atomic number Z, so Z number of protons in it, then how much will its charge be? Charge will be plus Ze. And let's say there are electrons revolving around it. Consider a single electron species. Okay. Consider a single electron revolving around a nucleus. Okay. Now, what helps it revolve around the nucleus is the electrostatic force of attraction between the nucleus and the electron. What is the formula for electrostatic force of attraction between two charges? F is equal to K Q1. One charge is the charge of an electron. The other charge is the charge of the nucleus divided by square of the distance. Assume it revolves in a circle of radius r. Then K E multiplied with ZE divided by r square. You can write this as KZE square by r square. This is the electrostatic force of attraction between the nucleus and the electron. If there is only one electron, this is the only force it experiences. If there are more electrons, no, electron repulsive force also will act on it. For now, we are not considering that. We are considering a single electron revolving around the nucleus. Then this force behaves as the centripetal force acting on the electron. So you can equate this to mv square by r. When r gets cancelled, you get mv square is equal to kze square by r. And divide this by 2, you get the kinetic energy of the electron. Therefore, the kinetic energy of electron revolving around the nucleus, that is half mv square, will be kze square by 2r. This derivation is very, very important because sometimes they give you some other model of the atom, okay, and ask you to find out what is the energy of that revolving particle or electron, whatever it is. But like they can replace the electron with something else and ask you to find out how much kinetic energy it has, potential energy it has, total energy it has. So you need to know how it is derived. So we start with the force that acts on the electron, equate it to centripetal force. From there, you will get the kinetic energy expression. Next, nucleus and electron are charged particles. Two charged particles, which are at a finite separation from each other, have a potential energy also associated with them. If the charges are Q1 and Q2, then the potential energy, electrostatic potential energy between the charges is calculated as K Q1 Q2 divided by the distance between them. And in the potential energy formula, you are supposed to substitute the charges along with the sign. Now in force formula, I didn't substitute minus E in place of charge of electron. I just took E. Why? Because we are only writing the magnitude of the force and equating it to magnitude of centripetal force. That's why I took the charge of electron as E. But when you express potential energy between two charges, you are supposed to substitute charge along with sign because potential energy can be positive, it can even be negative. Okay. So the potential energy between the electron and the nucleus becomes K Q1. One is the charge of an electron, which is minus E. Q2, the charge of the proton, which is plus, not proton, sorry, charge of the nucleus, which is plus Ze, divided by the distance between them. So the potential energy becomes minus Kze square by R. Okay. Kinetic energy is plus Kze square by 2R. Potential energy is minus Kze square by R. You can say that the potential energy is minus 2 times the kinetic energy. Okay. These ratio based problems are also very common. Even in chemistry, you have this. Okay. Now you know potential energy and kinetic energy, then you can tell the total mechanical energy of the electron revolving around the nucleus. Add those two, it becomes minus Kze square by 2R. So you can say that the total energy is negative of kinetic energy. You can also say it is half of the potential energy. Okay. And total energy being negative means it is a bound system. Okay. You learn the same in gravitation also. Uh, Satellite revolves around a planet under the influence of gravitational force. Okay. And there you would have derived expressions for kinetic energy of the satellite, potential energy of the satellite, and total energy of the satellite. You will see very similar expressions there. Okay. And there also, the total energy of a planet satellite system will turn out to be negative. It's a bound system, means the satellite will not leave the planet. It will keep revolving around the planet. Similarly, here we see that the total energy of the electron is negative, means the electron is not going to leave the nucleus. It is bound to the nucleus. To make the electron leave the nucleus and go away from it, you are supposed to make its total energy zero. Then it becomes independent of the nucleus. So you will have to supply energy to the electron to make it go away from it. Okay. So depending on the radius in which the electron revolves, this is the total energy. Fine. So remember how this is derived. We write the expression for centripetal force. Sorry, we write the expression for electrostatic force equated to centripetal force. From there we get kinetic energy. And for potential energy, we have a direct formula, electrostatic potential energy, K Q1 Q2 by X. Add them both, you get the total energy. Okay. Now, Rutherford's model of the atom obviously had some drawbacks, could not explain a few experimental observations. Okay. And theoretical concepts also, like electrons should radiate energy and fall off into the nucleus. Why that does not happen, could not explain. So then Bohr came up, Niels Bohr came up with another model of the atom. He said that what Rutherford proposed is correct. Okay, electrons revolve around the nucleus like planets revolve around the sun. Okay, but why they do not emit radiation? Why atoms emit only certain wavelengths? Why atoms absorb only certain wavelengths? He gave explanations for that. Okay, that is what is basically the Bohr's model. So Bohr's model is just like an addition to the to Rutherford's model of the atom. So first thing Bohr proposed is the existence of stationary orbits. Now, stationary orbits are basically stable orbits. Stable in terms of what? In terms of energy of the electron. So there are certain orbits, means there are particular radii, okay, in which an electron can revolve around the nucleus without emitting electromagnetic radiation. Okay, so basically these are orbits in which a revolving electron does not radiate energy. Okay. Now, why it does not radiate energy in these stationary orbits, that is not part of the discussion. There must have been an explanation, I'm sure. And again, for that, you need to understand quantum mechanics and all. Why are certain radii stable? Okay. That explanation is not part of your syllabus. You don't need to know that. So there are some orbits in which, there are some radii in which the revolving electron does not radiate electromagnetic waves, does not radiate energy. So it is stable in those orbits. Such orbits are called stationary orbits. Okay. Next. Sorry. What is special about these stationary orbits? Okay. He gave some explanation. He said that in stationary orbits, the angular momentum of electrons, angular momentum of the revolving electrons, is an integral multiple of h by 2 pi. Okay. Such orbits are stationary orbits, and in such orbits, electron does not radiate energy. So when the angular momentum of an electron is an integral multiple of h by 2 pi, automatically the orbit becomes stationary. Okay. And the electron does not emit radiation. Okay. Now, electron is like a point mass, small particle. What is the formula for angular momentum of a small particle or a point mass? Basically, it is m r, that is the position vector of that particle, cross v, the velocity vector of that particle. Okay. Now you have to take angular momentum about the nucleus. Suppose an electron revolves around the nucleus like this. Then with respect to nucleus, if you see, the position vector of the electron is this. This is r vector, and you can see the v vector. The angle between r and v is 90 degrees. Since the angle is 90 degrees, you can say that the magnitude of angular momentum, that is magnitude of mr cross v, becomes mvr. Okay, mvr sin 90, that is mvr. Therefore, according to the second postulate of Bohr's model, mvr, the angular momentum of the revolving electron, should be an integral multiple of h by 2 pi. So mvr is equal to nh by 2 pi. Very important and useful equation. Only in such orbits, the electron does not radiate energy. So he proposed the idea of stationary orbits, and he said what is special about stationary orbits also. Angular momentum is an integral multiple of h by 2 pi. Now, if angular momentum is an integral multiple of something, if any quantity is an integral multiple of something, we say that that quantity is quantized. Okay. Quantized means there exist certain minimum amounts of that quantity, and the total amount of that quantity should be an integral multiple of the minimum. That is what we mean by something being quantized. Like you have studied that charge is quantized. What does that mean? Charge, there is a minimum amount of charge that can exist in an object. That charge is the charge of an electron. Fine. And the total charge on an object is an integral multiple of the charge of an electron. Q is equal to Ne. You know this. Okay. So if there are definite minimum amounts in which a quantity can exist, and the total amount of that quantity is an integral multiple of the minimum, then we say that that quantity is quantized. In fact, the minimum amount that is there is called a quantum of that quantity. Now, Bohr proposed that the total angular momentum of an electron is an integral multiple of h by 2 pi. So the least angular momentum that an electron can have is h by 2 pi, and any other angular momentum is a multiple of that. So this is the quantum of angular momentum, h by 2 pi, and the quantity as a whole is quantized. So second postulate, you can also call it as quantization of angular momentum. Okay. Then the third postulate. The third postulate basically explains the atomic spectra, absorption and emission spectrum. Now see, there are only certain orbits in which the electron is stationary. Means the electron can revolve without emitting radiation. Right? And such orbits should satisfy these conditions. MVR should be equal to NH by 2 pi. So you consider a few electron orbits like this. Let's say this is one orbit that you see here. You can consider another orbit, maybe bigger than this. Fine. Now, why do atoms absorb or emit only certain wavelengths, not all? Basically, what he said is, when radiation is incident on an electron, okay, not electron, sorry, on an atom, radiation means what? Electromagnetic radiation, which is basically a stream of photons. Okay, last chapter we discussed the experiments based on photoelectric emission. They proved that radiation, when it interacts with particles like electrons, its particle nature is more significant. So you have to think of radiation as a stream of photons traveling towards the electron. Now that electron, which is in one of the stationary orbits, can choose which photon to accept and which photon to not accept. And the electrons will only accept or absorb those photons which will help them move from one stationary orbit to another stationary orbit. Okay, so the electron is not going to accept all the photons that you throw at it. it will only accept those photons which will help it move from one stationary orbit to another one. To which one it goes, that is not part of our discussion. There's a probability based calculation. You will learn that in engineering, not now. But the electron will only accept those photons which will help it jump from one stationary orbit to another stationary orbit. That is why a particular atom absorbs only particular radiations, particular wavelengths of radiation, not all. And the same can happen in reverse also. An electron which is in an excited state, a high energy state, can release photons, means it can release radiation and come down to a lower energy state. And in that process, the atom emits radiation. But the electron will emit photon only if it helps it lose sufficient energy to come down to another stationary orbit. So there are only certain energies of radiation that will be emitted. And if only certain energies are emitted, that means only certain wavelengths are emitted. So this is how Bohr explained the atomic spectra of atoms, why only certain wavelengths are absorbed and emitted by atoms. Okay, fine. The rest of the chapter is about the calculation of how much energy is emitted, absorbed, how much energy an electron has, all those things. Let us begin with that. Remember the three postulates. First, he proposed the idea of stationary orbits in which electrons don't radiate energy. Then he said what is special about these stationary orbits. In a stationary orbit, the angular momentum of electron is quantized. It should be an integral multiple of h by 2 pi. And atoms absorb or emit radiations, or absorb or emit only those radiations which help electrons jump from one stationary orbit to another. Okay, higher or lower, only those wavelengths will be absorbed or emitted. First, let's calculate how much energy an electron has in a certain stationary orbit. Okay, very, very important. The derivation is also important. Now, from Rutherford's model, by writing the centripetal force equation and all, we already derived that the total energy of an electron revolving around the nucleus is minus k z e square by 2r. Now, this energy depends on the radius in which the electron is revolving. Okay, wait, I think we should do that part first. We should derive the radius of stationary orbits. Then you can substitute here and tell what is the total energy of electron in the stationary orbit. Let's do that first. The electrostatic force of attraction between the nucleus and the electron, that is what is the centripetal force acting on the electron. So kz e square by r square is equal to mv square by r. Now, this gives us one equation which has two unknowns: the radius of the orbit in which the electron revolves and the speed with which it revolves. Okay. The other values are known to us. K is Coulomb's constant, m is mass of electron, z is the atomic number of the nucleus, E is the charge of an electron. So, depending on the radius, the speed varies. Now, Bohr proposed an additional condition. So, you take this as equation 1. The second equation we get from Bohr's postulates is that mvr, the angular momentum of an electron revolving in a stationary orbit, should be equal to nh by 2 pi. This is another relation between the speed and the radius. Now, if you have two equations with two unknowns, you can solve them. So, from the second equation, you get V is equal to nh divided by 2 pi mr. Substitute this in the first equation, you will get an expression for the radius of the nth orbit. Let us do that. So, you get kz e square divided by r is equal to m v square. V square becomes n square h square by 2 pi whole square is 4 pi square m square r square again. Okay, cancel one m, cancel one r, and make r the subject of the equation. You get r is equal to n square h square divided by 4 pi square m kz e square. So this is the expression for radius of the nth stationary orbit in which an electron can revolve. Okay, n can be any integral value starting from 1. So on. If n is equal to 1, okay, we call it as the first orbit. N equal to 2, second orbit, and so on. Okay. Now, this is all valid. This formula is valid only when this is the force acting on the electron, right? Kz e square by r square. This should be the only force acting on the electron. And when will this be the only force acting on the electron? When there is only one electron revolving around the nucleus. Okay. So whatever we derive based on Bohr's postulates is all valid for a single electron species. For example, you can use it for hydrogen atom directly. Hydrogen atom is the simplest of all atoms. It has one proton and one electron revolving around it. That's all. It doesn't even have neutrons. The nucleus has a proton. The proton itself is the nucleus, and around it an electron revolves. That's the hydrogen atom. Then helium. Helium atom has two protons, two neutrons, and two electrons revolving around it. But if you remove an electron from helium, it becomes helium plus. Helium plus is a single electron species. You can apply Bohr's model to helium plus. Okay. Then lithium. Lithium has neutral lithium atom has 3 electrons. You remove 2 electrons, then it becomes a single electron species. So to such what do you call? To such species, you can apply Bohr's model. Basically, there should be a positive charge with a single negative charge revolving around it. Okay, and if they want to twist and ask you questions, they can replace the electron with some other particle. They can replace the nucleus with something else and ask you to find out or derive how much is the radius of the stationary orbit and so on. Okay, that's why the derivation is important. They can even give you a modified form of Bohr's model. Like Bohr said angular momentum is quantized nh by 2 pi. They may give you, consider angular momentum as n square h by 2 pi and derive an expression for radius of the nth orbit, energy of the nth orbit. Okay. Any such changes can be made. Okay. Now, n is the orbit number. We can substitute. Depending on which orbit's radius you want to find out, you substitute n. Done. H is Planck's constant. Yeah, not a big deal. We can substitute. We know the value. We can substitute. M is mass of electron. K is Coulomb's constant. Z is the atomic number. And E is the charge of an electron. So atomic number and the orbit number are the only things which can vary in this formula. So you can write R is equal to, okay, the radius of the nth orbit is equal to h square divided by 4 pi square mk e square. These are all constants multiplied with n square divided by z. Okay. And if you substitute all these, you get this as approximately 0.53 angstroms. Okay. Therefore, the radius of the nth orbit in a single electron species is equal to 0.53 into n square by z. Okay. Suppose you take the hydrogen atom. Okay. First orbit of hydrogen atom. First orbit means n is equal to 1. Hydrogen means z is equal to 1. Therefore, the radius of the first orbit of hydrogen atom becomes 0.53 angstroms approximately. Okay, it's actually, I think, 0.529. We'll take it as 0.53. This is called Bohr radius. radius of the first stationary orbit of hydrogen is called the Bohr radius. Okay. And any other stationary orbit's radius can be expressed in terms of this, as you can see here, 0.53 into n square by z. Okay. So you can even say that radius of the nth orbit, radius is proportional to n square divided by z. Questions based on this are very common. They'll give you the radius of a certain orbit of one atom, and they'll ask you what is the radius of some other orbit of some other atom or the same atom, such things. Okay. Let's solve one question based on this quickly. Derive the radius of the third stationary orbit of helium plus. Do this quickly. Okay. Tell me the formula for radius of nth orbit. General formula for radius of nth orbit.
0.53 into n square by z.
Okay. Now we want radius of the third stationary orbit. So n will be substituted as 3. So n square, 3 square divided by z. What is the atomic number of helium?
2, sir.
That's all. So why will it be 0.26?
Yeah, sir, I put 3, 1 instead of 3 by mistake.
Okay, fine, fine. Simplifying like this calculation will give you the radius of the required orbit. So this way you can find out radius of any stationary orbit in a single electron species. Okay. Ratio based questions are also quite common. They can ask you what is the ratio of first orbit of hydrogen to third orbit of helium plus or lithium plus, lithium 2 plus, whatever it is. Okay. So remember the formula 0.53 n square by z. Based on that, you can answer these questions. Next, the energy of an electron in a stationary orbit. Now we have an expression for the radius now. N square h square divided by 4 pi square mk ze square. If you have an expression for the radius, you can tell the expression for energy directly. In Rutherford's model, we already derived that total energy is minus kz e square divided by 2r. If you know the radius, you can tell the energy. That's all. So we'll plug in this value of radius here. Therefore, total energy of the electron, the sum of kinetic and potential energy becomes minus kz e square divided by 2 times of that radius expression, n square h square divided by everything. I'll send it to the numerator, 4 pi square mkz e square. Okay. 2 and 4 cancel, 1 2 remains. Therefore, the total energy of electron becomes minus 2 pi square, a complicated expression, m k and k square, z and z square, e square e power 4 divided by n square h square. Now, depending on which atom and which orbit's energy you want to find out, you can write this total energy as minus 2 pi square. M is the mass of an electron, K is Coulomb's constant, E is the charge of an electron, H is Planck's constant. So these are all fixed. Multiplied with Z square by N square is what you'll be left with. Okay. And all these constants, if you substitute, it becomes minus 13.6 electron volts. Okay, we discussed this unit of energy, electron volt, in the last chapter also. So the total energy of an electron in the nth orbit can be expressed as minus 13.6 z square by n square in electron volts. Simple formula. And again, this is valid for a single electron species only. Okay. So if you consider the first orbit of hydrogen, then the total energy becomes, first orbit means n is 1, hydrogen means z is also 1. The total energy becomes minus 13.6 electron volts. Any other orbit, you just substitute the corresponding n value and z value, you can tell what is the energy of electron in that particular orbit. Okay. Generally, like you can see here, suppose the orbit number increases. Okay. If orbit number increases, this fraction will decrease. But there is a negative sign before the fraction. That means the total energy increases as the orbit number increases. Fine. That means the higher the orbit in which the electron revolves, greater its total energy. Okay. So n is equal to 1 corresponds to the least energetic state of the electron, least energetic orbit of the electron. Okay. So generally, n is equal to 1 is called the ground state. In any atom, the first orbit in which an electron revolves, the energy of the first orbit is called the ground state energy. Okay. Or when electron is in n equal to 1, we say electron is in the ground state. Okay. N is equal to 2 corresponds to higher energy than the ground state. We call it as first excited state of the electron. Excited means having higher energy than ground. Okay, so n equal to 2 is the first excited state. N is equal to 3 corresponds to the second excited state of the electron, and so on. Okay, getting excited means getting more amounts of energy, right? So now we have a proper value for the energy of electron in any orbit. And if you know the energy of electron in any orbit, you can tell how much energy it gains or loses when it jumps from one orbit to another orbit. Okay. For an electron to go to higher orbits, it should gain energy. For an electron to jump from higher orbits to lower orbits, it should lose energy. And in what form does it gain energy or lose energy? In the form of radiation, electromagnetic radiation. So gaining energy means it absorbs photons. Losing energy means it emits photons. This is how you can find out the exact amount of energy that the atom radiates. And for every photon that is released, you know energy of a photon is given by hc by lambda. Okay, is equal to hc by lambda. If you know the energy with which the photon is released, you can tell the wavelength of radiation that is emitted. Or if you know the energy of the photon that is absorbed, you can tell the wavelength that is absorbed. This way, we can even tell what are the set of wavelengths that a particular atom will absorb or emit. So we can explain the atomic spectrum. Okay, both absorption spectrum and emission spectrum can be explained on this basis. Okay. Suppose an electron jumps. Okay. Suppose electron jumps down from orbit number n1 to orbit number n2. N2 being smaller than n1. So suppose an electron jumps from a higher excited state to a lower energy state. Right? Higher orbit to a lower orbit. Then what will happen? Higher the orbit, greater the energy, lower the orbit, lesser the energy. So it is jumping from a high energy state to a low energy state, means it should radiate energy. Okay. Then in this step, okay, as it jumps from higher orbit to lower orbit, the energy emitted will be energy that the electron had initially minus the energy that the electron has finally. That's the energy it would lose. And we have a formula for energy of the nth orbit, energy of electron in the nth orbit minus 13.6 z square by n square electron volts. So in the first orbit, in the higher energy state or in the higher orbit, its energy would have been minus 13.6 z square divided by n1 square minus final energy that the electron has will be minus 13.6 z square by n2 square. Okay. Simplify this. It becomes 13.6 z square into 1 by n2 square minus 1 by n1 square, and all this is in electron volts. Okay, not in any other unit of energy. Now, in what form is this energy released? In the form of radiation. So this energy will become the energy of the photon that is released. And we have a formula for energy of photon, hc by lambda. So you can equate this to hc by lambda. Okay. Therefore, you get 1 by lambda, that is the wavelength that is emitted. Okay, so 1 by lambda emitted when an electron jumps from higher orbit to a lower orbit becomes 13.6 divided by hc z square into 1 by n2 square minus 1 by n1 square. And last chapter we discussed hc in electron volt nanometer is around 1240 nanometer. Okay. Sorry. Simplifying this or substituting the atomic number Z and the orbit numbers N1 and N2, you can tell what exact wavelength is emitted when an electron jumps from higher orbit to a lower orbit. And you will get the answer in nanometers. Okay, because that 13.6 is in electron volts, electron volt cancels, you will get the wavelength in nanometers. Is this clear? Any doubt in this? Okay. Now, this can be expressed in a slightly different way also. We can write 1 by lambda, okay, that is the lambda emitted, wavelength emitted, is equal to Rz square, where R is called the Rydberg constant. Okay. Rz square into 1 by n2 square minus 1 by n1 square. And Rydberg constant R is approximately 1.01 into 10 to the power of 7 meter inverse. So if you substitute this value of R there, you will get the wavelength in meters. Okay. This formula is very important. It can help you derive the wavelength of radiation that will be emitted when an electron jumps from one orbit to another orbit, from a higher orbit to a lower orbit. Okay. Let's solve some problems based on this, or fine, we'll stop it here for today. It's already past 7:30. Next class, we'll solve problems based on atomic spectra. We can discuss something called spectral series of hydrogen atom also. Lyman series, Balmer series, and so on. Questions based on that are very common. In fact, in this chapter, mostly the questions will be from that part itself. Okay. Either calculations based on Bohr's model or atomic spectrum. Okay. Those are also calculations based on Bohr's model only, but they use this formula. And it's very simple. Okay. So we'll discuss all that in the next class and we'll finish this chapter.